Good afternoon, everyone. My name is Ming Ma. I come from Rensselaer, and I'm very excited to be here this afternoon to share with you my invention and the stories with my invention. So the title of my presentation is Brighter and Smarter Light-Emitting Diodes via Graded Refractive Indexes. So I think we're all familiar with light-emitting diodes, or LEDs. I'm glad to see that it's already been used in one of our invent team's invention. And so what I built is a light-emitting diode, so LED is a type of light source. So let's have a look at it. So on this photo is a LED chip, which has a size of around 1 centimeter by 1 centimeter. And on this LED chip, there are two types of LEDs. One of them is regular LEDs. And the other type of LEDs, which is shown inside this red dash square, are graded refractive index LEDs, or green LEDs in short. So you can see that the difference between green LEDs and the regular LEDs is that the green LEDs have these special coatings on top of them. And these coatings have graded refractive index. And these coatings make them look different than regular LEDs. And I will give more details about these coatings later. But for now, that's not the only difference between green LEDs and the regular LEDs. Next slide, please. Yes. The green LEDs improved performance of LEDs in two ways. First, it emits about 3 times, as much as 3 times more light than regular LEDs. So green LEDs are brighter LEDs. And in the meantime, secondly, the emission from green LEDs are more uniform and more controllable than regular LEDs. So that makes them smarter LEDs. Now that you have seen it, let me share with you how I invent this and the lessons I've learned during the invention process. Let me start with the motivation of this invention. So I live off campus, and I drive to work every day. Sometimes when I work late and come back, it was already in the evening, so the street light was on. So this was taken at the street on my way back in an evening. And I think everybody should be aware, should be familiar with this type of illumination. But let me just ask you, what is wrong with this picture? Yeah, I think you might have already noticed. There are regions that are very bright, but there are also regions that are totally dark. And we have this type of illumination for decades, and we're getting used to it, but I don't think this is really what we want. And especially by me, because when I was taking this picture, I was actually standing in one of those totally dark regions. And so there are cars coming and going, and I'm not really sure they can see me. So I was kind of risking my life taking this photo. So I meant it when I said I was glad to be here today to share this with you. So this is not really what I want. Can I go back to the last slide? Thanks. This is not really this type of illumination is not really what I want. And so it naturally comes out that I would like to invent something that can change this. I want a street that is uniformly illuminated. There's no totally dark spaces here. So I think the lessons I've learned here is you need to be aware, because the invention means to solve a problem. But this problem might have already been in your life. It have already been in your everyday life that you just might not notice yet. So in my case, I drive on this street every day. And I noticed this problem, and I want to invent something to solve this problem. Now let's come to the second point. Now we want to solve this problem, and the second step is how we're going to solve it. So in order to come up with an idea, I think the second lesson I've learned is you want to be open. What I meant is you want to be open to ideas that might seem have nothing to do with your problem. In my case, I want to solve an LED problem, but actually in the end, the solution comes from something that is totally irrelevant. And so people have been telling me you should be thinking out of the box, you should be thinking, like you should be looking into the sky. So I took their advice literally. I looked into the sky, and I found my solution in the sky. Actually, in the Earth's atmosphere. So the problem actually, in short, it can be summarized to the way to solve this problem is to reduce reflections. And people have really found that back in 1880, Lord Rayleigh has already found that the Earth's atmosphere, there's no reflection. And was later found, the reason is because the Earth's atmosphere is not just one layer of gas, but it has several layers of gases. And more importantly, those layers of gases have their own refractive index. And they're decreasing with the altitude. So when it goes higher and higher, the refractive index goes lower and lower. So we call this type of refractive index graded refractive index. And that is the solution to my problem because this type of refractive index profile have no reflections. So actually found solution to my LED problem from Earth's atmosphere. So what I want to say is the lessons I've learned here is you want to be open to all kinds of ideas, even though it looks totally unrelated. Next slide, please. So the concept goes to how we apply this to LEDs. So the initial thought is just have this graded refractive index coatings on top of it. But later is find out that if we go ahead and pattern them into arrays of micropillars, in this way we can have better control of it, and we dramatically increase the surface area. So it actually has better results than we expected. So we successfully apply this concept onto the LEDs. Well, at this time we already have a concept, but how we really put this on a real device. That comes to the third lesson I've learned. That is, you need to be persistent and patient, just as this cat here. Well, the Earth's atmosphere, it took it about 2 billion years to form what this looks like now. I only have 5 years, so my time is a little bit short. But what I want to say is, whenever you have unsuccessful samples, don't give up, but learn from it and just keep improving. I just want to show you here the evolution of the green LEDs I have been fabricating. So this, on the left-hand side, you can see is what we expected. Very sophisticated, well-controlled shapes. And on the right-hand side is reality. So this is what we got in the first. I don't know if you can see it, but this is really messed up. So if I stopped at this time, there'll be no green LEDs, and I won't be standing here. So what we did is we found out the reason, and we kept on improving this, and this is what we got next. A little bit better. Now at least you can see the shapes, but still, on the regions that are not covered, they're still kind of messy. And if I would have stopped here, I won't be standing here today too. And what happens is we learn from this again and again, and in the end, we successfully fabricate what is very close to what we have designed. And just show you how small are those features. They're actually on the scale of 5 micron. So how large is 5 micron? On the left-hand side is magnified human hair, and it has size of 80 micron. So if you put those small pillars back to back, 16 of them would be the same size of human hair. So it's kind of really, really small features. So it's very understandable that they have unsuccessful samples. But what we did is just kept learning from it and kept improving it. And in the end, we get some really nice results. Well, I kept using we in the sentence because I could not have done this just by myself. And I'm really lucky to be in part of a team, which includes myself. And all these people I've been interacting with, my advisors, the senior researchers in our research group, and my colleagues, ex-colleagues. So I've been really lucky to be in such a team. And I also want to point out the variety of backgrounds in my team. You can see here, there are people from different backgrounds like electrical engineering, material science, and physics. So you really can benefit by talking to different people and by interacting with them because they also provide different aspects because they are from different background and you can also get their aspects. So that's really beneficial. I think to sum up, the lessons I've learned is that first you need to be aware of the problems because you might have already been experiencing it in your daily life. Oh, sorry, go back, please. And you want to be open to ideas, even though it might seem totally irrelevant with your problem. And you want to be persistent because more often than not, they're going to be stuck with unsuccessful samples at first, but they just keep on improving it, learn from it, and in the end, you'll get what you want. And in the end, just to be part of a team because this really, you can learn a lot from team members, especially from team members from different backgrounds. I just want to take this opportunity to thank Mrs. Dory Lemelson and the Lemelson Foundation, and also the Lemelson MIT program to giving me this opportunity to be here. I'm really glad. And in the end, I just want to say that I've been having fun in the invention process, and I hope you will have the same fun too. Thank you very much.
Thank you. That was a really great presentation, Mr. Ma. My question is, so I saw that you've been successful in your fabrication after repeated trials. You've been able to get, so that it exactly matches the conceptual, the animation that you had on screen. So have you been able to move past the fabrication stage onto more of an integration into an actual LED, or is that current research that's going on right now?
Well, that's a good question. So actually, this is a very practical device because LED is actually going to end up being used in people's everyday life. So what we do is we're actually in collaborating with LED manufacturers, and actually they're testing my device and to see if it's compatible with their process and how is it compatible with their final packaging. So to answer your question, yes, we have been testing them.
My question is regarding light pollution. I know you're looking for the uniform illumination of things such as streets. Mm-hmm. Could that present a problem if you're totally saturating the nighttime with light?
So the question was, would the uniform illumination become kind of light pollution? Yes, I think that is a good question, and actually, there's one thing I did not point out here. Not only more uniform, but this green LED is also more controllable. So that means we can control the emission pattern. So we can control to whatever shape we want. And this is achieved by, you see there's a lot of sophisticated structures there. For example, the four-pointed star structure, which I showed here. But there are also other structures. So by varying those structures, you can have control of the emission pattern. So you can design an emission pattern that fits your needs, and then you design a structure that can achieve this. Yes.
What is the lifetime on these LEDs?
Well, actually, that's a good question. LEDs actually, compared with conventional lights, or such a fluorescent light bulb or incandescent light bulbs, LEDs actually have much longer lifetime. And actually, I think the average lifetime of current LEDs is like 5 to 10 years. And after that is also one key issue in my invention, because I don't want to degrade this advantage of LEDs by putting those structures on them. So I have actually tested the device, and it shows that no degradation have been done to the LEDs. So the lifetime will not suffer from all these processes. Oh, thank you very much for your attention.